Hi, everybody. I'm just letting y'all know we're going to have our exam 3 review this coming Sunday. Our room got double booked for our usual time, so we had to move it to Sunday because we lost a coin toss. It's still at the same time, 7 to 9 p.m. and in the same room, double 107 Fiedler Hall in the engineering building. Since it is on Sunday, I know a lot of people don't like that because there's a football game going on and no one really wants to come during that. So I will try to post the exam we're going to do before the review. And then I'll also post the solutions after the review is over. And I'm going to try to find some way to record it, but I can't guarantee that because most of the stuff to record things have been sent away since things are back in person. So I'll let you guys know on Teams whether I'm recording or not. And thank you, and I hope to see most of you guys there.
All right, thank you, Gabriel. So we'll also have a class review next week. So class review. This will happen again on Wednesday. I think I'm going to do this from 6 to 7 p.m. and I'll send the Zoom link. So Zoom link. I'll put that in an announcement probably this afternoon. Okay, so yeah, it's flying by. With last regular exam for the finals, but we'll have a good space in between. Okay, so today is the last bit of material that will be on this third exam. I also should mention there is a written practice exam that's available now on the module in Canvas, so you can feel free to go check that out. There's a solution set there as well. If you see any issues with the solution set, please let me know. It's sort of, I didn't do a lot of editing on it from last time, so sometimes mistakes carry over. All right. So what I wanted to do today is do a little bit more with this linear change of variables. I think that, again, that's what I've found to have the most difficulty for students to have a lot of them struggle with kind of finding these. So last time we did a problem and I wanted to talk a little more about it. That was a problem of integrating over sort of a diamond. We had this region R. It was this kind of picture here, 2, 0, 0, 2, 0, minus 2, and negative 2, 0. And one of the steps in the solution to the problem was to find, well, I should say A, linear transformation from the square, which is sort of centered at the origin, 1 and minus 1, etc. To this 2R. So I kind of wrote it down when I was doing the solution without too much explanation. So let me try to explain one more systematic way of doing it than what I just said, hey, let's notice this and this. So what I did say is I said, well, if I take this point, I can find some linear transformation sending to that point. And I can take, if I take this point, I believe I took this point here and sent it here. So I kind of, the one I gave sort of reflected and then rotated maybe a little bit, scaled a bit too. So how would we find that if we didn't sort of just guess the answer? Well, for this, you just you remember again this general form. So I know that my general form for linear transformation is AU plus CV, BU plus DV. And what I do is kind of what I did yesterday, but now I'm not going to put in these I and J, I'm going to put in these particular red and blue vertices that I want. So I'm going to say, well, I want this red vertex 1, 1 to go to the red vertex 2, 0. So I want this. So I'll just force it. And when I put 1, 1 into T, I'm going to get A plus C, B plus D. And I also want this blue vertex 1 minus 1 to go to 0, 2. So I know that I want it to go to 0, 2. I put it in T1 minus 1, and I'll get A minus C and B minus D. And what this, so these are actually 4 equations in 4 unknowns, and they're linear equations, but you can sort of break them up into 2 equations and 2 unknowns, 2 sets of 2 equations. In particular, if we just look at these x coordinates, we'll get these 2 equations. We get 2 equals A plus C, and 0 equals A minus C. Now, if you're taking some linear algebra, you know that there's kind of a nice matrix way of solving these equations. But for things this simple, you know, you can see that the second equation says A equals C. And then you can put that second equation into this first equation. You have 2 equals A plus A, or 2A. So that you have A equals 1, and then C equals 1. So the x coordinates give you these 2 equations, and then the y coordinates are not that much different. We get a B plus D and a B minus D. The B plus D equals 0, B minus D equals 2. So we don't get B equals D, we get B equals negative D, or vice versa, D equals negative B. So let's say D equals negative B. And then if we put that into this equation, we get 2 equals B minus negative B, or 2B. And we get the B equals 1. But then that means since D equals negative B, that D equals negative 1. So let me just say, you know, what you're aiming to do here is, right, we're asked to find this linear transformation. And we know the general form. So what that's really asking is, what are these coefficients? What are these as numbers? So you want to find those numbers. And what I'm describing here is the method to find those numbers. You prescribe where the points go, and then you solve some equations. They're not hard equations. They're always going to be kind of simple linear equations. And so once we've got that, we can rewrite T. Putting in our values for A, B, C, and D. So we have A and C are 1, so we get U plus V, and B is 1, so we get U, and V is negative 1, so we get minus V. And this is what I believe I wrote yesterday. It's by eyeing it, but it's a more systematic kind of method. Questions about this? Should we do another one, or do people feel really good? We can do something like with triangles or something. People okay? What do people want? Yes, triangles? Okay, triangle, great. Let's do triangles. All right, let's, I'll give you a triangle on an unrelated problem, but this one on the practice exam. So let R, oh, I don't want to use T. Let's let R. I call this R. Okay. Let R be the triangle vertices. -1, 2, 2, -1, and -1, negative. So find a transformation T from, I'm going to call it the standard, but I'll explain what I mean. Standard triangle or simplex to R. So what is the standard triangle? Well, okay, it's not so standard. I mean, people will call this the standard simplex, different things. But one version of it would be just take your basis vectors 1, 0, and 0, 1, and take the origin, and then just fill it in. So that's what I mean by this. Call this S. Okay. This one's kind of maybe too easy actually, but okay, we'll do it anyway. So let's draw this triangle R. Let's draw this triangle R. May help to have a little graph paper here. All right, so I've got coordinates. One is -1, 2. That's here. 2, -1. That's here. And -1, -1 is here. So now I can connect those. Nice. This is going to give me my triangle R. So I want to map this triangle to this triangle. So should I write down the formula for a linear transformation here? Linear map? And then try to do what I just did? Or should I not do that? How many people think I should do just what I did? How many people think I should not do what I did and do something different? How many people just want to get out of here? I don't see any. Half of, like, I saw 2 hands get raised for either option. All right. So you're supposed to notice something about this. If I want a linear transformation from here to here, there's an issue. Which I talked about last time, which is that all the linear transformations will send the origin to the origin, which means they'll send this vertex that's in the interior of this triangle to a vertex of the second triangle. That's no good. Not if I want a one-to-one function. So indeed, I shouldn't really be looking for a linear transformation, but I'll be looking for something very close, which is I'll take a linear transformation and then I'll translate it. That's it. So, and in fact, these two triangles look very, very close. One is just sort of a scale of the other, right? So what I would recommend here is I would recommend sort of, I mean, again, different problems require different sorts of solutions. So in this case, what I would say is I want to translate my rectangle R so that this vertex here goes to the origin. So I'll just add 1, 1. Does that make sense? Oops. I'll add 1, 1. And so what does that mean? This is a transformation. I'll call it T1 of UV, which is equal to U plus 1, V plus 1. And what that's going to do is it's going to take everything, bring it over here, and, well, okay, I just, here, That's what it's going to do. It's going to shift everything up one. But now I do have a vertex that's the origin. And this is, if I look at this new rectangle, or new triangle, pardon me. There was a football game a long time ago. I don't remember when, it's been years. And it was a big football game, and I guess Nick Saban was coaching. You guys know who Nick Saban is, I guess. He's kind of famous. Alabama's football coach. And he said, what did you tell your players before this game? And he said, told them, because it was an away game, and he said, I told them, don't worry, it's the same triangle we play at home. And the sportscaster afterwards said, well, it doesn't look like he's very good at math. And my wife said, that's basic shapes. That's not math. Our 1-year-old at the time can identify a triangle versus a rectangle. Well, okay, but who am I to criticize Nick Saban? Maybe they do play on a triangle in Alabama. Who knows? Anyway, I just made the same mistakes. Okay, so this triangle is a scale, right? This guy now has 3, 0, 0, 3, 0, 0. This is a scale of S. So if I want to go from here to here, you can basically guess, I think, the linear transformation. Just scale the coordinates by 1/3, right? Take 1/3 of everything. That'll scale this down here, this down here, and everything. This will go down to here. And 0 will stay at 0. So here we can multiply by 1/3. So T2 of u, well, I don't know, u tilde, v tilde, just equals 1/3 of each. 1/3 v tilde. Running out of room here. So if you do both of these operations, then you'll get, and you just compose, start here, go here, and then go here, you'll get this transformation. And so how do you do it? Well, you just compose. So T of uv is going to equal 1/3 of u plus 1, 1/3 v plus 1. Or if you want to write it out, 1/3 of u plus 1/3, 1/3 of v plus 1/3. Not a linear transformation. So if you had started out trying to solve this for a linear transformation, you would have had some difficulties. But once you add that translation bit in, it's not so bad. Clear? Okay. All right, good. So now, what we want to do is we'd like to go up 1 dimension and have a little more fun, because it's too not very interesting in just 2 dimensions, right? So last time we said if we had one of these nice 1-to-1 differentiable functions, 1-to-1 onto, at least on the interior, then we had this beautiful, wonderful theorem of double integrals, which was just, okay, I'll write R here, f of xy, dx dy equals f of xu v, f u v. Now we had to add this factor of the Jacobian of t, du dv. Now we're doing this over S. Now we can take this and we can do this, so this holds, I want to say, or the appropriate general form of this holds in any dimensions, any dimension. So in particular, the dimensions we're most interested in this course to get ourselves comfortable are 2 and 3. So we can easily make this adjustment, well, at least almost easily, but we have to do a little bit of adjusting. So here we're going from a 3-dimensional region to another 3-dimensional region. So our x, y turn to x, y, and z. Our u and v are going to turn into u, v, w. So we have an extra coordinate in the other variables as well. Our Jacobian is just a Jacobian. However, and we take the absolute value again. However, this Jacobian is now the determinant not of a 2x2 matrix, but a 3x3 matrix, the total derivative of t. So the Jacobian here is the determinant of a disaster. You can imagine how disastrous it is. So del x del u, del x del v, del x del w. Make sure it doesn't matter so much, but I want to keep consistent here. The y del u, the y del v, the y del w, del z del u, del z del v, and then del z del v. So this is what the general 3-dimensional change of variables looks like. The main case, okay, so you can certainly do linear changes of variables in 3 dimensions. So if you had some strange 3-dimensional integral over a parallelepiped, you can do either a linear or a linear in a translation to get you down to this sort of a square box, or just the unit cube if you want. So that's possible. It's, again, things get a little more complicated. Before you had to solve linear equations of two linear equations and 2 unknowns, now you'll have to do 3 and 3 unknowns. But again, it's not out of the question. But I would say the main application, or the most common way you use a change of variables in 3 dimensions, certainly in this course, and I think in some applications such as physics, would be to go to spherical coordinates. So let's derive the change of variables formula for spherical. And if you're worried, you should be. But it'll all turn out all right in the end, I promise. So we need our transformation t. So certainly it's easy when you go to spherical or polar or cylindrical coordinates. Of course, you use different things. We don't call them u, v, and w. We call them whatever we're calling them. And usually we don't put the x, y, z in here. We'll put the variables in here. We'll think of f as a function of those variables, and we sort of just put the variables u, v, w in there, whatever u, v, and w are. So the hard part here is not really writing this in. The hard part is computing that, or at least the computationally intense part. So we need this change of variables, t of rho theta, or phi theta. So I chose this order, I believe. Well, we'll see. If I chose a different order, I might get a negative sign, but that's okay. I'm going to take absolute. So this is going to be these three different functions, which are given by the equations for spherical coordinates, which are always in those tables in on the exam and so on. So if you'll recall, or even if you don't, what this is going to be rho cosine of theta, and then a sine phi. This will be rho sine of theta, sine of phi. And finally, we'll have rho times cosine of phi. So what we're going to need to do is figure out what this matrix looks like and then take a 3x3 determinant. So, you ready? Nope. Okay. Bear with me. So I need your eyes so that when I make mistakes, you guys can correct them. All right, so I'm going to take the derivative with respect to rho first, and I'll go column by column. So if I take the derivative of rho of x, and then y, and then z, I'm just going to get rid of the rho in each case. So that will give me a cosine of theta sine phi, sine of theta sine phi, cosine of phi. Okay, that wasn't too bad. Now I'm going to take the derivative with respect to phi. I'll go down the line. So I'll get a rho cosine of theta cosine phi, a rho sine of theta cosine of phi, and then a negative rho sine of phi. Then finally, I have to take the derivative with respect to theta. So I'll get a negative rho sine theta sine phi. Rho cosine theta sine phi, and then 0. No theta here. Does it look right? Did I make a mistake? Questions? Okay. This is the derivative, total derivative of this change of variables. Not the most pleasant thing to look at. It's okay. Now we want to take the determinant. So let's take the determinant. So what do we do to take the determinant? Well, we take this guy. We have to do the usual bit. Take this guy, cross out, and take the determinant of this thing. Okay, we can do that. Cosine of theta, sine of phi. This isn't so bad. This is this times 0. That's 0, right? Minus this, minus this times that. So I've got a negative of a negative. That's rho squared cosine of theta sine squared theta. I don't know if I want to write sine squared theta, but I will. Sine squared phi, pardon me, sine squared phi, not theta. Okay, then I go to this guy, cross out the top, cross out that, and take the determinant of what's left. Again, I've got some nice things. I've got 0 here. I've got to add a negative sign. I get rho cosine of theta, cosine of phi. And again, I get 0 minus, well, I've got a minus, rho cosine theta, cosine phi, sine phi. Okay. Just strain my eyes a little bit. Okay, that's all right. And finally, got this guy. This guy's not as pleasant as those other very pleasant ones. I've got a plus, but I've got a negative. So let me get the negative. Rho sine of theta, sine of phi. And now I do have to do something, right? So I get a negative rho sine squared of phi sine theta minus rho sine theta cosine squared of phi. Okay. Then I'm going to add these up. So this is my first term. This is my second term. Nope, leave it. I'm gonna have to get rid of that. And this is my third term. All right, let's see what we got here. So we got a minus and a minus. That's plus. This is parentheses. I've got another minus and a minus. Well, okay, I've got a minus and a minus here, so I've got a plus. And now I can look inside this last parentheses here, and I see a cosine squared plus sine squared times rho sine theta. So that's just 1. So I get here plus rho sine theta squared, rho squared, sine phi. That simplifies. Okay, what about these first two terms? You see anything? Anything lovely? I see a cosine squared in both of them and a rho squared, right? Cosine squared and a rho squared, right? And then outside of that, I see also a sine, cosine phi squared and a sine phi. Oh, wow, look at that. What a lovely thing. So I see this, okay, so let me simplify this. Let's write this down. Let's go rho squared, cosine squared, sine phi, sine squared. Here I get a rho squared, cosine squared, sine phi, cosine squared. These are the same. So I get the same factor here and here times a sine squared plus a cosine squared. That's pretty good. So I can simplify that, and I'll get a rho squared cosine squared theta sine phi. It's simplifying pretty well, huh? So the first term is coming from these two, and the second term is coming from this last term. Oh, but now I see a rho squared sine of phi times cosine squared plus sine squared of theta. Right? Okay, so it was horrible. It was bad. It was bad. I feel like I did something wrong just by showing you this. I apologize. Don't tell administrators. I'll get in trouble. But there it is. And now we have our formula. Integral of f dx dy dz. Questions? It's equal to the integral over whatever spherical system we have of f rho phi theta, but now we add the absolute value of the Jacobian. Do I need an absolute value? Question to you. Do I need an absolute value? I do. I don't. Who says I need an absolute value? Who says I don't need an absolute? Wow, it's pretty even. Well, you could have an absolute value, but you don't need it. Why? We're in spherical coordinates. The angle phi, this azimuthal angle, is between 0 and pi. The function sine between 0 and pi is positive or non-negative. So this is always going to be non-negative for the spherical coordinates. So we don't actually need to put in an extra absolute value. It's already non-negative. Just like r. We didn't need one for r dr d theta, right? So here we also don't need one. Pretty good. Pretty good. All right, let's do a problem. We just derived some expression. Let's see if we can apply it. So as you'll see on this important concepts, right, there's also this one for cylindrical coordinates, not so bad, right? That's just a pretty clear generalization of the polar version. So I'm not gonna spend much time on that, at least in lecture, but there it is. Let's apply this one for spherical. Okay, so we've already done this once, but let's do it again. Calculate the volume of a radius r, capital R, ball. So a ball, we might as well center it at the origin, right? No problem there. And if we're calculating volume of a particular region in three-dimensional space, that's the same thing as integrating the function 1, right? So the volume of our ball, let's call our ball B for ball, not for box, is going to equal the integral over B of dv, which is dx dy dz. Now in spherical coordinates, what is B? This is ball. It's this kind of operator overloading or something, notation overloading. This is ball in XYZ. However, in spherical, what is this? Huh? Rho? Just rho. Well, we have. So if you wanted to, if I wanted to specify a ball of radius r in spherical coordinates, I need to, it's not just one coordinate that you're specifying. You're saying, you know, you've got 3 coordinates. What are they? In spherical coordinates, I want to say this is a box. This is a spherical box. You remember we talked about polar rectangles? This is a spherical box because we can let our coordinates, if I'm using this ordering of coordinates, which I will, vary. Rho can vary from 0 to r. Phi can vary from 0 to pi. And theta can vary from 0 to 2 pi. Right? Any values within, for the spherical coordinates, our ball is a box. This is the beauty of coordinates. So if we convert this using our change of variable formula into spherical, we'll get the following integral. With respect to rho, we go from 0 to r. With respect to v, we go from 0 to pi. With respect from theta, we go from 0 to 2 pi. We have what's our integrand? It's 1. But we have to add our new change of variable factor. Oops, d rho. Okay, well, I can integrate with respect to phi. That's pretty easy. Got an iterated integral here. Integral of rho squared is rho cubed over 3. I'm evaluating from rho equaling 0 to r. I've still got my sine phi sitting here. D phi, d theta. So this is going to give me r cubed over 3. That's a constant, right? R is the radius, so it's not changing. I can pull that out. I'm integrating from 0 to pi of sine phi d theta. Integral of sine is not a hard thing to calculate, right? Negative cosine. Pi to 0. At pi, cosine is -1. At 0, cosine is 1. So that's 1 minus -1, which is 2. So I will get a 2 factor here times the integral of 1 d theta, but that's easy. That's just 2 pi. So, not bad. I didn't have to do weird bounds. I didn't have to like integrate over a disk with I mean, everything is, once I can integrate over a box, life is very easy, especially if you've got an easy integrand. So that was not too bad. Should we do another problem? Sure. We could. Let's do it. But of course, I really do not want to forget to add this correction, add this Jacobian. You've got to try to remember to do that, because without it, you're going to be making mistakes. You will not get the correct answers. All right, so let's do one more problem, a little less simple, but not too bad. So let's let R be the following region. We'll put it in Cartesian coordinates, x, y, z. We'll put a couple of bounds, x squared plus y squared is less than or equal to z squared. And we'll say that x squared plus y squared plus z squared is less than or equal to 1. So then calculate the integral, triple integral over this region of z dv. I believe we did something like this when we were doing triple integrals over more general regions. Okay. So what is this region? What is this region R? What is this region R? People know? If you go over to Call Hall, you get one of these. Huh? Get a little ice cream cone. Because we know that if we look at this equality here, this is actually just this big cone here. And let me actually, to make it an actual ice cream cone, let me assume that Z is greater than 0 too. Sorry, I'm going to add that in. So now if Z is positive, what I'm going to get is I'm going to get this region here for the first inequality. But now the second inequality tells me that the distance between the point and the origin is less than or equal to 1, which tells me that I'm inside of a ball of radius 1. So there's sort of a top here. So I'll just draw it. So this is sort of this is the picture we have. So now that we have the picture in mind, we should see, or you should see, that that spherical coordinates are the way to go here. So if you don't see that right away, take a minute and think about it. We're bounding our radius, rho. Once we have this bound, any rho will do. You can scale by rho. There's a theta independence. We rotate this thing around the z-axis, it stays stable. So theta is just going to go from 0 to 2 pi. And this last bit, phi, is really just going to be described by an inequality here. If I'm here, I can let phi vary as long as it doesn't surpass the angle between this line and the z-axis. So in fact, you can write this down as a set of, so in spherical coordinates, you'll get the following bounds. And again, you have a spherical box. You have rho is between 0 and 1. That's just telling you the bound for your radius. Theta, well, maybe we can do phi. So phi is between 0 and pi over 4. And then theta between 0 and pi, or 2 pi, pardon me. So why this pi over 4? Well, if you look at this, this is calculating this angle here. But if you look at this, this first equation, or this first inequality, and take square roots of both sides, you're going to see that the square root of x squared plus y squared, if the bound is achieved, is equal to the absolute value of z. And this is just r, the radius in polar coordinates. So this line here is going to be essentially, this picture here is going to be like the absolute value function, that profile. So it's a slope 1. If you're looking at the positive part, this is slope 1, which means this angle is, pi over 4, 45 degrees. Half of pi over 2. Is it okay? You can also do this with just equations and solve, put in spherical coordinates and solve, but I'm just trying to give you a picture here. Okay, so that's for this. Once you have that, then again, you can set up this integral quite easily. And we'll just set it up, and then you can see that it's not going to be a hard one to solve. And we'll leave it at that. So here we're going to go, we've got this factor of rho squared sine of phi. That was our Jacobian. We've got d rho, d phi, d theta. So my bounds are going to be 0 to 1, 0 to pi over 4, and 0 to 2 pi. But now you do need to remember, you're not always just finding volume. You need to put your integrand in. And so this z is now z as a function of the spherical coordinates, which is just coming from that table. So this is going to be rho cosine of phi. But again, this is not a hard function. Cosine of phi, sine of phi is like a half sine 2 phi. So you can do that. And then we get some rho cubed here, some power of rho. So you can do this. So I'm out of time, but you can solve that if you'd like. All right. Have a good weekend.